So Newton's second law on a particle says that if F is the force on a particle, then F is equal to the rate of change of its linear momentum, so ddt of mv. So that means you get ma. So this m into v is known as the linear momentum of the particle. Now this was Newton's law for a particle, single particle. Now let's apply, or let's extend this Newton's second law for a system. Newton's law for a system of particles. Now we'll give a very simple example at first, then I will generalize. So suppose these are, say, two blocks are connected by a spring, say block of mass m1 and block of mass m2, and there is an external force F acting on block m2 only, and say there is an extension in the spring, so spring force kx, and here also spring force kx. So say a1 is acceleration of, say, m1, and say a2 is acceleration of m2. So a1 and a2 are acceleration. So this block is having acceleration a2, and this block is having a different acceleration, say a1. So what we can write for block 1 and block 2? For block 1 and block 2 we have to write the force equations. Block 1, only the spring force acts, so kx equal to m1 a1, and block 2, F minus kx equal to m2 a2. Now if you add up, you get F equal to m1 a1 plus m2 a2. So this is actually the Newton's law, or this is how it's modified Newton's law for the system. Now we can generalize it for n particles in the following way. See, now this case will deal with Newton's law for a system of n particles. Now a system is a region in space of your choice, and suppose the system shown here, this dotted line shows the system. So inside this system there are n particles, so of masses m1, m2, m3 up to mn. So suppose this is one of those, say m1, this is 1, m2, and say this is m3, this is m4, m5, like this up to n particles. Now there is an external force acting on the system. Say this is the external force Fext. This may be a contact force like pushing, pulling, or maybe a non-contact force like gravity. Okay. Now consider, say, on the forces on the particle 1 having mass m1. So a fraction of this external force may act on it. See, either the whole external force may act or a fraction may act on it, right? So we can write in general that it's a fraction of F external by this one. This is the diagram. This force shown the fraction of the F external. Fraction may be 1 also. Right. Now see, also on this mass m1 or this particle 1, there may be internal forces due to particle 2, say 2 attracts or repels, whatever. So there are these internal forces like this due to other particles. So let this So let us write this internal forces. In general, we can say internal forces may be there. So this is F I N T, internal. So internal forces on M1 due to other particles in the system. So now we can write here, say for particle M1, Newton's law. So fraction of F external, this is for M1, right? For particle M1, fraction of F external plus F internal, that is the sum of the internal forces due to the other particles, is equal to M1 times A1. So A1 is the acceleration of particle 1. So here also we can mention A1, A2, A3 up to AN are accelerations of particles, so M1, M2 up to Mn. Okay. Now similarly for M2, what we can write? Again a fraction, maybe a different fraction, plus F internal equal to M2A2. So F internal on 1, this is F internal on 2. Similarly we can write, say for M3 we can write fraction of F external again plus F internal on 3 equal to M3A3. So if you go on writing all this up to n terms, so what do you get here? So if you add all the fractions of the external forces, you get the total external force on the system, F external. See, the summation of the internal forces is 0. Now here what you get, M1A1 plus M2A2 plus up to MnAn. So this is the thing we have derived just now. For the n particle system, if the net external force on the system is Fext, then this expression F external is summation of Ma. So M1A1 plus M2A2 plus M3A3 like this. So this is the expression for Newton's law for a system, Newton's second law for the system. So this we can again write like this, F external is equal to so Ma is ddt of M1 V1 plus ddt of M2 V2 plus M3 V3 like this, ddt of Mn Vn. So this again we can write it like this, the differential sign here, and we can add up the things, M2 V2 plus Mn Vn. So that is F external. This is by the simple rule of differentiation, right? So but the simple rule is that, say dx1 dt plus dx2 dt you can write as ddt of x1 plus x2. Very simple rule of derivative. Okay, now we can write, see this M1 V1 plus M2 V2, this one up to mn vn. This is the total linear momenta. Momenta is plural, momentum is singular, right? Total linear momenta of system of particles. Okay, so now if f ext equal to 0, if f ext is equal to 0, then derivative of a certain thing is 0 means this part is constant. If f ext equal to 0, then m1 v1 plus m2 v2 plus up to mn vn is constant. So this is, we have proved that, we have actually proved the conservation of linear momentum. So that is it actually. We will put it into words. This is what we have proved, that if f ext equal to 0, then sigma mv, or the summation of the linear momentum of all the particles of the system, is conserved. So this is the principle of conservation of linear momentum. So this we can see. If so, now we'll state the principle of conservation of linear momentum. So if the net external force on a system is 0, then the total linear momentum, total linear momentum of the system is conserved. I think I've mixed up the singular plural. The total linear momentum of the system, that's okay. Now we can write that total linear momentum is equal to the sum of linear momenta. Now it will be plural, sum of linear momenta of all particles in the system. Sum means vector sum, actually, all particles in the system. Yes. So sum means, actually I should have written vector sum. So that total linear momentum of the system is the vector sum of linear momenta of all particles in the system. So we have proved the conservation of linear momentum here. So we'll show some simple examples of conservation of linear momentum. So the first example is that of a collision between two particles or two balls. So this green one is ball A, pink one is ball B. So ball B is at rest, ball B at rest, and suppose they both are kept on floor. Both are kept on smooth floor, B at rest, while ball A approaches at speed 10 meter per second, collides with B and gets stuck to it. Find the find their common velocity. Their common velocity after impact, or after the collision rather. So this time they will stick together, and the masses are given. So m1, that is mass of A, is 5 kg, and m2, mass of B, is 10 kg. So here what will happen after the collision? So this is the situation shown before collision, and the situation I'll show here. This is a drawing after collision. So after collision they will have the same speed, because it is given they will stick together, so these will both move with the same velocity v each. So let v be velocity common after impact or after the collision, right? So here so as there is no external force on the system, whatever force acts is between the balls A and B. So there will be force between balls A and B. Ball B, so this is to the left, this is force on A due to B, and here also you have force on B due to A, but the net force is 0. So the net external force is 0. These are all internal forces. So we can conserve momentum. So momentum before collision, or initial momentum, equal to momentum after collision, or final momentum of the system. So that implies before collision momentum for block A or ball A is 5 multiplied by 10, for B is 10 multiplied by 0, and now it is 5 multiplied by V plus 10 multiplied by V. That means 50 is equal to 15 times V, implies V is equal to 10 by 3 meter per second. Now this second example is related to an explosion. Here a bomb, obviously it's kept in gravity free space, or it's kept on ground. A bomb explodes into two equal fragments. Two of these move perpendicular to each other with same speed v0 each. Find velocity of the third fragment. Now one thing we have to mention, the bomb at rest. A bomb at rest, then it explodes into three equal fragments. So that is it. This is the bomb before explosion, and this is after explosion. Two of the parts move up at right angles. So this is these two move at 90 degree. Say this is the x-axis and this is the y-axis. So this is having so suppose the mass is 3m. So the mass is 3m. So this is moving with mv0. This is also moving with mv0. And let's see where the third part moves. Now the vector sum will be 0. The vector sum of the momenta of the particles will be 0, because it was 0. And so in the explosion there is no external force, all internal forces. So suppose this is, so we name this P1 momentum, P2. So we have to find out P3. momentum of the third part. This P1 plus P2 plus P3 will be equal to 0. So that means this is P1 is this, and P2, if you apply triangle law, this P2 is this, and then to make it 0, P3 will be this. So let's put the vector signs P1, P2 and P3, and their magnitude, that is mv0, this is mv0, this is m times root 2 v0. So P3, so the third part will move in this direction with the speed how much? V is v0 root 2, because momentum of the third part P3 is equal to m times v. Let v is speed of the third part, third fragment. So that is m root 2 v0, implies v equal to root 2 v0.